Now let's talk about particles moving with constant acceleration. So if you have a situation where a particle is moving with a changing acceleration, that's very difficult. It's complex to analyze. So this one, where the particle is moving at constant acceleration, is a simple kind of one-dimensional motion. In this case, you will see that the instantaneous acceleration ax is equal to the average acceleration ax avg. Remember, for example, if your grade in math is 95, your grade in science is 95, your grade in calculus is 95, the average is 95. And also, all your individual instantaneous grades are 95 for each subject. So, for example, if your average acceleration is 3 meters per second squared, for a particle under constant acceleration, at each instant of time, the acceleration is also 3 meters per second squared. So the velocity, if we look at it in terms of the velocity changes at the same rate. The change is constant. That is the particle moving under constant acceleration. So remember, this is the formula for average acceleration, but we equate it to instantaneous acceleration because, again, they are the same. And here, delta t, which is supposedly tf minus t initial, we will from now on set ti equal to 0. So that, and we also set tf equal to t. And that will simplify our expressions for the formulas that we are about to derive. So, actually, if we rearrange this, we come up with our first formula for objects moving at constant acceleration. In this formula, if you know the initial velocity, the constant acceleration, you will get the final velocity at any time t. Let's look at the graphs here. No, look at the graph part B. You will see that the slope is constant. And in a velocity time graph, remember that the slope is the acceleration, right? If you look at each instant of time, the slope is constant. And this graph implies constant acceleration. If you look at the third graph, ax over t, we see that in this acceleration versus time graph, the graph is a horizontal line. This implies that the slope is 0, which means that the acceleration is constant. So for acceleration versus time, this is what constant acceleration looks like. Horizontal line. Okay, so for position versus time, we'll learn more about this in the next slide. But this is what it looks like for constant acceleration. And we have another formula. This is the second formula. Vx equals Vx initial plus Vx final over 2. So this only applies for constant acceleration. For example, if your initial velocity is 3 meters per second and your final velocity is 6 meters per second, and you want to know what the constant acceleration is. Remember, we have to assume that the acceleration is constant. You can just get the average of those two velocities, and that turns out to be 4.5 meters per second squared. Remember, this formula only applies for constant acceleration. There's another formula. If we combine this last one that we derived with this standard definition for average velocity, we will get this equation. I will not go into the details, but this equation will help you get the final position xf. If you know the initial position, you know the initial velocity, the final velocity, and the time. That's the third equation. And this one is the fourth equation, which you can derive from this first equation, substituting it into this third equation, and then making some algebraic changes, you will get this equation. This equation is actually, it has a t squared, no? Do you see that? That implies, t squared implies that if we graph the position versus time, that you will get a parabola. So this one here is a parabola. So for an object moving at constant acceleration, if you plot the motion in a position versus time graph, you will get a parabola. You remember that in a position versus time graph, slope represents velocity. So if you get the slope at time 0, this slope represents the initial velocity. And at a later time t, if you get the slope at that point, that will give you the final velocity. It's a parabola, right? And then we actually can derive one more formula, and we will get this next equation. Vxf squared is equal to Vxi squared plus 2axf minus xi. And again, we make other derivation. No, this is not a derivation. This is just showing that when ax equals 0, if we substitute ax equals 0 here, some terms will be canceled. So these are your constant acceleration equations, two of them. If you substitute 0 for acceleration, then you will get these formulas. And if you remember, these are formulas for constant velocity. So that means that the objects are moving with no acceleration. The speed is constant. Like if you graph it in a velocity time graph, will look something like this, no? No, I'm sorry. It looks something like this, a flat line. My apologies. But if the acceleration versus time graph is plotted for constant velocity, the line will lie in the t-axis and will have a value of 0 for a. These are the 5 equations that you can use. These are known as kinematic equations. Okay. The way you strategically use these equations is you have to read the problem to understand what is given, and more importantly, to understand what is not given. Because for example, if in the problem it is stated that the acceleration is constant, but nowhere in the problem did it give you what the value for that acceleration is, you can use the third equation, 2.16, because this equation doesn't have a in its expression. There's no acceleration variable, right? So if your problem does not provide the acceleration, maybe this is the best equation to use. Sometimes though, you need to use 2 equations for 2 unknowns, depending on how complex the problem is. But remember, class, these equations only work if it is stated explicitly in the problem that the acceleration is constant. If the acceleration is changing, then that's for another, that's another thing, no? Okay. Some examples of particles moving with constant acceleration are maybe problems of cars accelerating at a constant rate along a freeway, or if you drop an object in a absence of air resistance, That object is called a free-falling object and has a constant acceleration of 9.8 meters per second squared downward. So let's just look at some problems. Here's the first problem. No? So a jet lands on an aircraft carrier at a speed of roughly 63 meters per second. So the question is, what is the acceleration if it stops in 2 seconds due to an arresting cable that snags the jet and brings it to a stop? So you have probably seen movies or television shows in which a jet lands on an aircraft carrier and is brought to rest surprisingly fast by an arresting cable. So if you read the problem carefully, you will see that the initial speed of the jet plane is 63 meters per second and the final speed is 0 meters per second because it is brought to a stop. And it is a good assumption that this motion is along the x-axis as the plane lands and is brought to stop at the horizontal platform of the aircraft carrier. So we don't really know what the displacement of the jet is. We don't know its final position. Its initial position we can set to be equal to 0. Once the jet lands, that our initial position, we can set that to 0. But our final position is not given. What formula can we use? If you go over the 5 formulas, you will find that this is the best formula. This was derived from Vxf equals Vxi plus A sub xt. But rearranging to solve for Ax, what is the acceleration? And we will find that the acceleration is negative 32 meters per second squared. Notice that we use this formula because it doesn't have a xf, doesn't have the xf variable. And so that's a good choice of formula. Because we are not given xf, so let's choose a equation that does not have xf. So if the jet touches down at position xi equals 0, as I mentioned earlier, now it's time to find for xf, and we can use this formula. I think there are multiple formulas we can use, but for this particular moment, let's use that formula. Will give us 63 meters. That seems reasonable, no? When it comes to sizes of aircraft carriers, 63 meters is a reasonable stopping displacement. However, no, if the jet lands at a speed faster than 63, it will have a larger x final, and the jet might overshoot the aircraft carrier. That will be tragic. Now let's try to solve this complicated problem. You are driving a constant speed of 45 meters per second when you pass a trooper. So a trooper is probably a police riding a motorcycle on a hidden behind a billboard. So you are driving at constant speed, and then all of a sudden, the trooper tries to catch up with you, probably because you are overspeeding. After 1 second that your car has passed the billboard, the trooper sets out to catch you, and the trooper not understanding that he is behind, he decided to move at constant acceleration of 3 meters per second squared so that he can catch up with you. So the question is, how long does it take the trooper to overtake your car? So the book has this strategy, no? You have to define certain things. First, you have to define where your t equals 0 is. When do you start considering time equals 0? And according to this reference, this book, they decided to set TB equals 0 at that moment when the motorcycle is, when the car is 1 meter away from the billboard. So T equals 0 is the time when the car has already moved 45 meters, right? Because um 1 second pala. 1 second after 1 second after passing the billboard, the trooper starts catching up with you. So after 1 second, the car has already moved 45 meters, right? Because the speed of the car is 45 meters per second. So once the trooper decided to catch up, that's the time we set our initial time to be 0. But also once the trooper decides to catch up, the car has already moved 45 meters. So the car has a head start of 45 meters. And let's see how that let's see we're solving for TC, no, the final time. How long does it take the trooper to overtake the car? So there are we have two formulas to use. This one is for the car, right? Because the car, this is the constant velocity model, no? Constant velocity formula. There is no acceleration here. X car equals XB, so plus VX car T. What X car here is the final position of the car. This time, this is the position that the trooper has already caught up with the car. XB, this is the initial position of the car. And our initial position is XB right here when it is already 45 meters, when it has already moved 45 meters away from the billboard. VX car is the constant velocity of the car. This is 45 meters per second. Time here, this is what we are looking for. We don't know what time this is that that our trooper can catch up. This is the formula that we will use for the trooper, right? So our XF, our final position, we call that X trooper. This is the position that the car and the trooper already meet. And here is our XI, the initial position of the trooper is 0 because we define, like if we set up the x-axis, oh, that's not really straight x-axis, but this is where the trooper starts at xi equals 0. This is where the car is, when the trooper is at xi equals 0, the car is at xb, which is 45 meters. So our origin, we set that to where the trooper is behind the billboard. The initial velocity of the trooper is 0, right? The acceleration of the trooper is 3 meters per second. But simplifying, we will find that this simple equation, x trooper is equal to 1/2 axt squared. We can actually equate x trooper and x car because remember, they both refer to the position where the trooper finally catches up with the car. So we equate them. And so we have this 1/2 axt squared is equal to xb plus vx car. And we are rearrange further, we rearrange, and we notice that this is a quadratic equation. And so to solve for t, we have to use the quadratic formula, negative b plus minus square root of b squared minus 4ac over 2a. Our b here is this one, negative bx dx car. our C is negative xb, and our A is 1/2 ax. And if we do that, we will get, with some more manipulation, we will get 31 seconds. Okay, so this is one of the more complicated problems, but that's all. Thanks for watching.